Let's get started. Let me tell you first of all what a string graph is. Okay, so this is a very natural notion. It's the intersection graph of continuous arcs in the plane. So here are a bunch of continuous arcs. Some of them intersect other ones. So you can build the intersection graph. So to every arc, you associate a vertex, and you connect two of them if they intersect. Right? That's a string graph. Okay. Important note, string graphs are not planar graphs. They're drawn in the plane by definition, but they're not planar. For instance, I mean, if you change this graph a little bit, you will get K5. This is a complete graph on 5 vertices, which is a string graph. Okay, so string graphs can be dense, for instance. Strings are not very special here. You can see that once you have strings, you can really consider the intersection graph of any set of path-connected regions in the plane, just by filling them in with a string. Okay. So just some indication that string graphs are a little bit subtle. It's known, for instance, that if you want to have a string graph on n vertices, then you might need 2 to the n intersections between the strings. In particular, that means that it's not clear that, for instance, the string graph recognition problem is in NP, because the natural representation is not polynomial sized. In fact, the recognition problem is NP hard, and even decidability was only established about 10 years ago. And now it is known there's a different representation which is polynomial sized, and these are the publication dates because logically it doesn't make sense for one to precede the other. Okay, so as Crystal said, what I'm going to talk about is a generalization of the Lipton-Targent planar separator theorem, that in any n-vertex planar graph there's a balanced separator of size square root of n. So what is a balanced separator? It's order root n vertices whose removal breaks the graph into 2 pieces, each of which is, say, at most 2/3 of the graph. Okay. So if you wanted to generalize this, for instance, to string graphs, and I'll tell you where it came from in a second, you see that there's a problem because, well, I mean, the complete graph is a string graph. Obviously, it doesn't have a balanced separator of size smaller than linear because it doesn't have any non-trivial separators. But Janos Pak and Jacob Fox made a very nice conjecture that all string graphs should have balanced separators, but now the size of the separators in terms of the number of edges. Okay? So at least for planar graphs, this is the Lipton-Targent separator theorem, and for complete graphs, this is just the trivial fact that there's a linear size separator, but at most a quadratic number of edges. But those are two very different reasons to have a separator of size square root of m. And the conjecture is that such a separator always exists. They proved a bound of m to the 3/4. Their applications were mainly sort of what they had in mind was in topological graph theory, crossing numbers of graphs in the plane, connections to other things. As Christos mentioned, Jirka made a sort of a very, almost the entire sort of step to the end here, and got square root of m log m for this problem. I mean, Matuszek was an amazing scholar, and unfortunately he left us in 2015. And I learned about this result. This is one of the last things he published at his memorial conference. Janos Pak gave a talk about those things. And it was also my first time in Prague. And it also happened that Jirka was using some methods that we developed with Satish Rao and my student many years ago. So this was like really an awesome gift to try and get rid of. I'd never been to Prague, and I had Jirka's paper, and there's an obvious log m to try to get rid of. I mean, you put all these things together, it's like a fantastic thing to try. But let me tell you, there's a sort of more general setting in which things work out. So it's the notion of a region intersection graph. So a graph G is a region intersection graph over a base graph G naught if G is the intersection graph of connected subsets of G naught. Okay, so you associate to the vertices of G connected subsets of the base graph, and then you put an edge between them if those 2 connected subsets intersect. So, okay, you'll see what it means if we just look at, say, okay, so an example, string graphs are and I've used this acronym RIG for a region intersection graph. So string graphs are precisely region intersection graphs over planar graphs. Here's the construction. Take your strings, put a vertex at every intersection, and then put an edge between all 2 vertices that are adjacent along some string. Okay, so then you get this graph. And now, for instance, now the corresponding regions, I mean, this green string, it corresponds to sort of the region which is this set of 4 vertices. And and this purple one is this set of 3 vertices. And you can see it's not too hard to convince yourself that the strings intersect if and only if the corresponding subsets of vertices intersect. So this is the setting we're in. And you can consider, instead of, you could, for instance, one class of graphs you could consider are strings drawn on, not in the plane, but on other surfaces. So there's many things you could think about. Here's the main theorem that if G is an intersection graph over some base graph G naught, and it has m edges, and G naught has some nice structure, for instance, if it excludes an H minor, then G has balanced separators of size square root of m. Where the constant here depends on the minor that the base graph excludes. So this gives you the gives you the full Pock and Fox conjecture because, well, planar graphs exclude a K5 minor, so that tells you that all string graphs have separators of size order root m. And another thing it does is, for instance, if you think about it, although maybe to speed things up, we won't go through it. This also generalizes the Alon-Seymour-Thomas theorem, just because every graph is a region intersection graph over the graph where dot G, where you subdivide every edge into 2. So you replace a vertex by this region. Now G is an intersection graph over this graph, and these graphs basically exclude the same minors. So you get Alon-Seymour-Thomas as well. So what was Jirke's approach? It's very simple. Given a string graph, you want to show that it has small separators. So the first thing you do is show that there's a good fractional separator, some linear programming relaxation of a separator. Then you round it to an integral separator. That's the argument. This step, you get the tight bound of root m. I'll explain the steps in a second. This step, you lose a log m. And so what we're going to do today is shave this log m factor. I actually don't remember. Was it you that when this conference was conceived, who was posted? There was like a competing conference called Slogan, which was about shaving log ends.
Yeah, that was
so, yeah, we've all come together. Okay.
Should not have saved the whole log m, right?
I think that's the threshold for ITCS. If it's less than log m, it's a technical contribution, right? Okay, so here's the approach. First, you show there's a good fractional separator. This is going to be quick. So, what's the dual problem to a fractional separator? It's a flow problem. So you try to send an all pairs multi-commodity flow in G, and you want to minimize the vertex congestion. So L infinity here means the maximum congestion. To show that there's a small separator, you need to show that there's lots of congestion for every all pairs flow. That's the sort of duality. So here's the argument. If you have a small congestion flow in G, this gives you a flow this is what Jirke did, gives you a flow in the base graph, not with small congestion, but with small L2 congestion, which is not defined, but you can imagine what it means. You sum over all the vertices, the sum of the squared congestions. And then he used the results that we proved with Biswal and Rao that, for instance, for a planar graph, if you try to route some flow with like a dense demand graph, then it has large L2 congestion. So that's that gives you square root of m. You show how flows in G can be routed in the base graph. If you have a worst case bound on the congestion, then you get an L2 bound on the congestion, but certain base graphs don't support flows with small L2 congestion. So that's the first step. Then there's the second step to round to a fractional separator. So you can do it using embeddings. And what Matuszek did was just used didn't use anything special about the structure for this step. Just use Bourgain's theorem that applies to any endpoint metric space. So now you can say, okay, you want to get rid of this log n. That's what gives you the extra log m factor, the rounding using sort of this generic theorem. You'd like to get rid of the log n using the structure of a fractional separator. In many cases, this can be done. Like you look at the dual solution, you look at the fractional separator, and because the graph has some special structure, you can improve this log n. So let me just tell you why it doesn't work. Like why Jirke didn't do it. So it just requires you to look at the distinction between edge separators and vertex separators. If you want to look at fractional edge separators, then the fractional objects are shortest path metrics where you weight the edges of the graph. And if you want to look at fractional vertex separators, the fractional separators are shortest path metrics where you weight the vertices. And those don't maybe seem so different, but the complete graph is a good example. If my fractional separator is an edge weighting of the complete graph, I can get any metric space by putting weights on the edges of a complete graph, any endpoint metric space on an end vertex graph. Just you take the distances, put them on the edges, that gives you the metric space. But if you only allowed to use vertex weights, actually, the fact that you have a complete graph means that you can barely do anything interesting. In fact, you always get something which is close to an ultrametric or an HST, just because the distance between 2 points is just the sum of the 2 vertex weights, which is proportional to the maximum of the 2 weights. So those are the class of edge-weighted metrics on the complete graph is the most you could hope for. I mean, if you were an adversary. And the class of vertex-weighted metrics is very small. So this suggests that there's a different theory for edge and vertex separators. So this is the penultimate slide. Here's sort of the fact we use that if G is a region intersection graph over G naught, and G has a strict H dot minor. Okay, so H dot is a subdivision of every edge of H. I'll tell you in a second what a strict minor is. Then H is a minor of G. Okay, so a minor of a graph means that you can obtain H from G by a sequence of vertex deletions, edge contractions, and edge deletions. A strict minor, you don't get to use edge deletions. So if you think about it's the analog between a subgraph and an induced subgraph. So now, so for instance, the complete graphs have have all the possible H minors, but they don't have strict subdivided minors, sort of just as an indication that, so this notion is different. So what's the last step if you want to do something? Well, now you have a graph with some forbidden structure. It doesn't forbid a minor H, it forbids a strict H dot minor. Can you apply some methods, can you do something with that? And so it turns out that the answer is yes. So let me not say anything about this, but for instance, the well-known method of Klein, Plotkin, and Rao, if you know it, then this slide probably gives you some kind of post-traumatic stress because it's learning that proof is it's a project that takes between 6 months and 10 years. But you can get the proof to go through. Basically, you do some partitioning, and instead of constructing a minor when the partitioning fails, you construct a strict H dot minor when the partitioning fails. So things go through. Okay, so let's conclude. There are a number of other applications. So lots of things you can do for minor free graphs or planar graphs. You can also do for these region intersection graphs. For instance, you can construct nearly optimal tree decompositions of those graphs. Here's a nice open question that maybe explains some of what's going on here. Is it the case that you can take, say, every vertex-weighted metric on a string graph and randomly embed it into planar graphs with constant distortion? That would give like a black box reduction that explains some of the results. That's very nice. And then, it seems like a joke to say is it related to string theory, and it is a joke. But if you're interested, I just posted a paper to the archive last night on using some of these methods in 2D quantum gravity. So it is kind of related to string theory. Okay, so let me stop there. Yeah.
Do you want to say a little more about your last comment?
I was going to ask the same.
No, but I'm happy to tell you. I have to talk about it during the break. So let's chat. Yeah.